have a friendly and relaxed, environment for the classroom. Okay, it's not like the old school professor. Hey, everybody, listen carefully. Okay, I will check your attendance first. Okay, first name. Okay, Tom, Peter, whatever, Jerry, and come see. Why we don't have enough students shows up? That's a bit weird.
Today's EMA day, right?
But the day ends at 2 p.m. Anyway, so before you leave, everybody tell your name, okay? Write your name on a piece of paper. I don't remove credit for people who don't attend, but for you guys, I give you some extra bonus. Seriously. So we should encourage instead of punishment. You know what I'm saying? That's a good point, right? So the game day today, and you still show up and devote to study and want to listen to when we're talking about this kind of thermodynamics, I give you some bonus.
So we should make an attendance sheet?
What's that?
Make an attendance sheet?
I will just put your name on a piece of paper. Yeah, exactly. But that after the class, okay, you can sign in and sign out. And everybody just come in. All right, so let's start. So briefly review what we were talking about last time. So we were talking about thermodynamics. And in thermodynamics, first law, basically, oh, by the way, I repeat it again, so why I'm wearing the stupid glasses today, especially for the online students, just in case you got really confused what happened. I cut my finger in the lab, okay, very long, and bleed a lot. And I cannot wash my hand for a period of time, but you know that this is whiteboard have a lot of the dust on my finger, I don't want to wash it. So that's the reason I'm wearing gloves, okay? I hopefully going to recover next week. And this is my graduate student fault. This is my postdoc fault, okay? I told him just to remove all the sharp edges on the instrument, but it still exists there. I just do not. Anyway. But luckily I'm a professor, they're working in the lab, so if I don't complain, if I don't report, nobody cares. But if students got injured in the lab, I will have trouble. So be very careful, Okay, you can never be careful enough to work in the lab, okay? Sometimes, even you follow the regulations, still sometimes the incident happen. It's not a very serious issue for me, but I know some very serious accident happen. For example, if you go through the safety training, you know there's a person got burned to death at UCLA. You heard about it, right? Yeah. And you know that there's a guy working on laser in the Los Alamos National Lab got got blind. You know, have you heard about it?
I think she died after 18 days, right?
I don't know.
No,
not die, but become blind.
No. One.
Oh, the UCLA. Yeah.
Yeah.
He works on some treatment. Anyway, so should be careful. I mean, although you can never be careful enough, some accidents still happen in the lab. But as long as you're not very fatal and damage for your entire life, except for cut the finger or whatever. But anyway, so that's the reason I have this glove. And I pay this glove myself with my own grant, so it's not consume the taxpayers' money. Okay, so it's not from your tuition either. But basically, it's from National Science Foundation. Okay, I use the money for the education. That's also good. Anyway, so we have enough present. Let's start talk about what we talked about last time. So we talk about the first law of thermodynamics, right? Basically, it's the conservation of the energy. And you know that basically we catalog the energy, internal energy, into two parts, right? The change of the internal energy has two contributions, right? Has two contributions. One is what? One is the change. One is coming from the heat transfer, right? So we label it as delta Q. And I have already explained why you delta instead of D here, because the Q is not the thermodynamic parameter, and the change we cannot. It's not it's not the well-defined derivative. Okay. And the other part is what? Is work, right? We introduce a negative sign because we define the object we under study and investigation as the object who give the work, who do the work, instead of receiving the work. Okay. So that's where we have negative sign here. Okay? So if the object doing some work to the external environment, it loses some internal energy. Okay? That's the reason we have negative sign. So this is the first law. And specific to gas, okay? Specific to gas, okay? Then we know that the du equals to delta Q minus PdV. Okay, P is the volume, P is the pressure, V is volume, dV is the change of volume, okay? And you can see right now we change this kind of, we can express this, the process parameter in terms of thermodynamic parameter, okay? And the original something is not different, it's just change variation. Okay, we change this variation in the precise form of the derivation, okay? They are derivative. Okay? So, but you can see if we write it that way, actually there's something in the textbook where people do not emphasize very precisely is that if we write it that way, we already assume that the internal energy is a function of T and V. Okay, it's already T and V. Of course, if the volume of the system doesn't change, if the volume of the system doesn't change, then the change of the internal energy is just equal to the heat transfer. Right? This is what we learn. But on the other hand, most of the case, in most of the scenarios, in our study, like the cooling or mixing the solvents, or mixing the alloy or whatever, we work at the atmosphere, right? The temperature doesn't change, the pressure doesn't change, but the volume changes, okay? This makes the job more complicated because if we want to study the change of internal energy, we also need to know the change of volume. So to address that problem, or to simplify the mathematical expression, we also define another parameter. We call it, what do we call it? Enthalpy, right? Then it can be expressed as delta Q plus VdP, okay? And by doing that, actually we assume that the enthalpy is a function of T and P. Correct? This is what we, I mean, basically, in the constant volume process, we prefer to use the internal energy as thermal parameter to describe the state of the system. And under the constant pressure system, we prefer to use the enthalpy. Okay, but it's not always, but this is just preferred, not necessarily absolutely yes or no. You still can use that one. For the constant pressure process, you can still use that one for the constant volume process, no problem. Just you want to make your life more miserable. Okay? But anyway, so for sometimes, for general case, the temperature change, the volume and pressure, all the parameters changes. Okay, so you just choose whichever you want. Okay. Okay. So and after that, this is the fundamental definition. Okay. For ideal gas. Okay. We also know from our discussion, we also introduce the concept of the heat capacity, right? And we know that for the ideal gas, this one equals to okay. It's not, I mean, because for the ideal gas, the U is not a function of the V anymore, right? It's not dependent on V. It's only a function of P, right? So actually, you do not need to write it in the partial derivative form. You can just use it write it in that way, because U is only a function of P, right? And for the CP, it's for that one, okay? And the same thing, H is a function of P, okay? And this is independent of P. Okay? So basically, for the ideal case, the V and P, they are constant. They're just constant, okay? And the volume and the internal energy and enthalpy only depend on temperature. But again, this only applies for the ideal gas, okay? And the relationship between Cp and Cv is just like R. We already mentioned this last time, correct? Everybody still remember? This was the talk last time. Okay, then the question is, what about for the general gas? What about none? So what's the relationship between Cp and Cv for real gas. Okay, for real gas. How can we, what's the relation for real gas? Okay, so this is the first question we're going to answer in this class. The reason we talk about this one is not only to explain what's the more general expression between these two parameters. The other thing is to tell you what another very important thing we want to introduce is how can we change the independent parameters for the thermodynamic parameters. Right now we're using T and V as an independent parameter to calculate the U, right? But as I mentioned, it's not always the case. It's not always necessarily the case. We can also select T and P to calculate the U. For that one, the same thing. We can also use T and V to do the job. Okay. But if we select T and P, the derivative of U cannot be expressed in such a way anymore, right? So what's the formula? Okay. So by answering this question, you will also learn the answer. How can we change the independent parameter for the U and H and other thermodynamic parameters in the future? Okay. So let's do the job. Okay, so let me just use my note. So in order to answer that question, so we know the definition of the Cp is what? Is the derivative of H, partial derivative of H as function of T, under constant pressure, right? As a constant pressure. We do not need to consider constant pressure only for real gas, only for ideal gas, but for the real gas, it's the partial derivative, okay? And in order to put the Cv, introduce Cv into this relationship, we know the definition of Cv is what? It's partial H, partial T, partial U, partial T, and the constant volume. Correct, everybody? So how to do the job? How can we link these two parameters? Okay, so we can do it that way. We know that this is H. The definition of H is what? Is that correct? Right? And more precisely, H is a function of what? Of T and P. Right? We select T and P as independent parameter. And then for that one, the U, the same thing. So we have to use T and P. Okay? Because the independent parameter for H is T and P, then we need to use T and P for the U as well. This, we already changed the independent parameter, right? We already changed it. And of course, plus P is an independent variable. We just keep it there. And V is a function of P and T. Correct, everybody? And we put this one, we put this equation back to here, okay? We put this equation back to here. Then we have Cp equals to what? Let me see what I'm doing right. Is the partial U, partial T, and we keep a constant P. Correct, everybody? And plus the P is the independent variable, so we don't worry too much about that term. Partial V, partial T, constant pressure. Correct? This is P. P, which has enough times. Okay. Is that correct? Right? Now think about it. And for this one, we already have the partial U, partial T this term, but we treat the P as a constant. If we want to introduce Cv there, we need to somehow change the formula. Okay, change the formula and introduce this one. So how can we do the job? So we can do it that way. So we know that U is a function, we know that we can write it in that way, right? U is a function of T and P, but we can also write it in some way, in something like this. U is a function of T and V is a first function of T and P. Correct? Will that work? Okay, so in that case, we only deal with this term. We only deal with this term. So think about it, how many parameters, how many terms have t here? So we have something like this, right? So first of all, we do partial derivative for this t here. So this one, then this one becomes partial u, partial t. And then we keep this term the same, right? We keep this term the constant. That is what? It's v, correct? And plus partial u, partial v as constant t times partial v, partial t as constant t. Correct? So if we change the parameter, the independent parameter, you're going to see that we use this technique. Okay, we introduce some intermediate parameter, v here. Okay. We express the u as function of t and p by introduce another intermediate parameter v, and the v is a further function of p and t. Correct? And then mathematically, if you want to do the partial derivative on the variable p, you need to do this part as well as this part. Correct? And sum them together. Then this term becomes this one. Okay? And of course, we add another term. Is that correct, everybody? Is that clear? And more generally, if you have a function fx, right? Fx, fx. We can express the fx as fg and x, right? Something like this, right? You can introduce another intermediate, okay? Then the df dx equals what? Equals the df dg times dg dx, right? The same principle here, right? We just introduce an intermediate parameter or function. Then this term is what? What is this term? X here, right? So this one is your resume, okay? And honestly, just don't know what I'm talking about. All right, so you can see it be a complicated term, right? So the relationship between CP and CV are complicated, right? So let's first off, let me briefly introduce or explain the meaning of each term. So first of all, look at this term. This is what? The constant P times the variation of the volume, induced by the change of temperature. So basically what? Basically this term is dV, right? The P dV is what? Is a work. Is a work done, right? Think about it. The heat got absorbed by the constant pressure process. Partially of it used to warm up the system, and the other portion of it used to do the work, right? And this term represents the work done by the system, okay? And the other thing is by changing the volume, if the volume of the system change, why does the internal energy have to change? And we mentioned last time, for the ideal gas, there's no potential energy between molecules, right? That means if the two molecules separate further and near and more close to each other, there's no interaction. The system doesn't change, the internal energy of the system doesn't change, right? But for the real gas, it's not always the case, because the atoms or molecules can repel each other or can attract each other, right? And this term represents that one. Okay, think about it. That means under constant pressure, we reduce the temperature and the volume change, right? And then this when the volume change, how the internal energy change. This basically, this term is the potential energy, right? This term is the potential energy, correct? Basically, this describes how the interaction between molecule change as a function of volume or as a function of temperature, right? This is the meaning of this. So basically, you can see that the difference between the constant pressure capacity and the constant volume capacity, the difference has two contributions. One contribution comes from the work done by the gas or system to the external environment. The other term comes from the change of the potential energy, the intermolecule potential energy. Okay? Is that clear, everybody? Okay, so this is for the real gas. But if this theory is correct, this should be all this equation should also apply to ideal gas, right? Let us see whether it's applied to the ideal gas. Okay, whether it's applied to the ideal gas. Think about it. We already mentioned that ideal gas we don't need to consider potential energy, correct, everybody? And we already mentioned this term it should equal to what? 0 for the ideal gas, because there's no internal potential energy or internal interaction between molecules, correct, everybody? So for the ideal gas, for the ideal gas, this term should become 0, right? And what about this term? So this term for the ideal gas, the P times partial V, partial T, and P. What this term equals to? P is there. We know for the ideal gas, PV equals to an RT. Correct, everybody? What about partial V, partial T? We mentioned that we define the V as a function of P and T, right? Then the V is what? V is what? Let me try. I forgot something. Okay. V is why? Give me a second. Okay. V is nRT divided by P, correct? And partial V, partial T, as a constant P is P nR. Correct, everybody? We put it back. This time equals to nR divided by P, so basically nR. Right? We put it back, we will have Cp equal to Cv plus nR. Right? This is correct for the ideal gas. That means if we apply the assumption of ideal gas to this equation, is turned back to the equation we introduced last time. Right? That means this is another way for you to double check whether your equations are correct or not. Okay? So this is the correct one. Questions? Is that clear? All right, so for next step, I'm going to ask you to do some practice, okay, to give you some trouble. We know that for convenience, we define the therapy, the enthalpy as a function of T and P, right? No. This is not what we can do. Okay. Remember last time for the ideal gas, okay? Remember that for the last time we talked about the ideal gas, okay? And we know that for this one, we already know that this one equals 0, right? For the ideal gas, right? This is what I already used here, right? And there's one argument. I ask you one thing is, what about this term? Okay? We know that this also equals 0. That's the reason I'm saying that I was saying that U is only a function of P instead of P and V. The reason is that there's only 2 independent variables out of 3, right? If we depend on T and independent of V, it must be independent of P. Correct? This is the argument. Right now, try to prove it. Okay? Try to prove it. Okay? The reason I'm asking you to do that is because for most of the case, we define U as a function of V and P, but in order to calculate that one, you need to use this expression, okay? Try to prove this one equals 0. I give you 8 minutes, okay? To finish the problem. So online student, let me know whether you can identify my handwriting clearly, okay? So if not, just drop me a message. Let me know if you have some issue with it. See that idea on the line? Instead of keeping all of them, I just keep going.
I thought I lost them.
No, they just forgot to take them away last time. Hey. You already recorded this part. I keep working on it. I just read something on the whiteboard for the online student to make the flow of the class clearer. we use the p as the independent variable for the u, right? So we can write it that way. So it's t and p, correct, everybody? And in order to use that one to prove that one, we need to somehow change this expression or include this one in the expression of this term, correct, everybody? The same technique. We know that the p, we can also write the p as function of t. Correct, everybody? Right? And then, what will happen? So that one. Partial u, partial p, and the, hold on. No. That's the correct? We can write it that way, right? In order to use the t and p as function, we can introduce the volume as intermediate. Okay? Let me write it properly. Right? And then this one can be expressed as partial v, partial u. The p is here. So in order to calculate that, we need to first of all do the derivative of v, right? And keep this one constant. And then do this term. Partial v, partial p. That correct, everybody? Huh? And this term equals 0. And this term equals 0. Simple. All right. Okay. So any questions? Just some trick, okay? All right. So similarly, prove partial h, right, partial v, for ideal gas. And let me give you the hint. So for in order to prove that one, it's not necessary. It is not necessary for you to write something. Of course you can, but it's not necessary for you to write something like this. Okay? It's not necessary for you to write something like this. Okay? Instead, starting from this definition to do the job. Okay? Start from here. Do you need more time? Okay, start talk about why the proof. Can we start talk about it? Yeah. So we know that we want to express h as a function of v, right? So instead of introduce the intermediate variable, we can use another way, right? So for the h, of course you can try, is a function of what? Right now, in order to prove that we need to select v and t as a variable, right? And now we can no way. Is that right, everybody? And then partial h, partial v, function of t will become what? Partial u, partial v as a function of t, plus partial p, partial v, constant t. Hold on, yeah, times v. And then we use the v as a parameter, and then plus p. Is that correct? We do the variation on this one. We do the differentiation on this one. Differential on p, partial v as function t, and also we have a constant p, v here, right? We know this term equals 0 from our assumption. Correct? And for ideal gas, p equals to what? nRT divided by v, right? And then, because of that, partial p, partial v equals to what? Minus nRT v squared, right? And then we will have v times partial p, partial v, p equals to minus nRT v, correct? And this one is what? This one is minus p, right? We put it back, minus p. Minus p positively cancel each other, right? Then this one equals 0, right? And the same argument is dependent on t, independent of v, so it must be independent of p, right? You can prove it yourself, okay? All right, so we finished 2 practice. Wait.
So I'm still writing.
Oh.
I have a question.
Yeah.
Conceptually thinking of it, like not looking at the math, but is it because in ideal gases, like there's no internal forces?
There's no internal.
That's why pressure and volume don't really affect it as much as temperature does?
Yeah.
Okay. Is that a better way to remember it?
It's better way to remember it indeed.
Okay.
And I'm going to, if I have time, I'm going to talk at the end of the class.
Okay.
Why is depend on temperature? Actually, for ideal gas, I'm not going to talk about ideal gas, okay? Not for other system. The temperature is a label of the average kinetic energy of the atoms. And for the ideal gas, we only need to consider the kinetic energy. There's no potential energy in the molecule, correct?
Is
So
it because they don't hit each other?
they hit each other, but they only at the solid ball, they just hit as elastic scattering.
You're talking about ideal gas, right?
Yeah, we're talking about ideal gas. So because temperature only label the kinetic energy, and ideal gas only have kinetic energy, then it only depends on temperature. Got the points? Yeah, because there's no potential or interaction between the molecules.
There's no work.
Exactly. Done? Okay, I'm going to erase that one, okay? All right, so sorry for give you so many troubles, but that's a way for you to practice yourself. And think about it. Practice problem, I mean, when you want to improve yourself, you always want to do some practice. And the practice is always a tough, boring, painful process. Always happen. So, but if you get used to it, you become very confident. And you learn something new. Anyway. So we're going to talk about something. I will still use the first law of dynamics, okay? Okay, we're going to talk about something. We're going to apply the same principle and consider some special case, okay? So one thing we want to introduce for next, we call it reservable. Reservable, right? Reservable or reserve? Is that right? Reversible? Means reversible? Yeah, I think something wrong. Reversible, yeah. I'm writing it out. Reversible, yeah. Reversible adiabatic process. So what does that mean? Again, we just apply the knowledge of thermodynamics and work and the heat to some special case, to some special thermodynamic process. First of all, what is adiabatic process? That means there's no heat change, right? We know that for the adiabatic, that means delta Q is to 0. Correct? Right now, consider we have a tank, we have a piston, we have a cylinder and piston on it. Okay? And then we just put some thermal isolation material as a foam or vacuum or whatever. We just put it here, okay? To make it thermally isolated from the environment. Okay? This is just a foam or whatever. So there's no heat exchange, okay? There's no heat exchange. There's no heat exchange anymore, okay? That's the reason the process inside it is adiabatic process, okay? And then reversible means what? We just press it down or release the piston, but there's no chemical reaction or whatever weird thing happening in the piston, okay? So we just press it or drag it, that's it, okay? So we have an ideal gas inside. So what will happen? So think about it. If I press the piston, what will happen inside? The pressure goes up, volume going down. That's the definition of pressure, right? Compress.
Temperature goes up?
Temperature goes up?
Yes.
Well, why temperature goes up?
More interaction happening?
Yeah.
Work done on the gas.
I mean, you are doing some work onto the gas, right? But why the temperature goes up? I mean, we know that from the thermodynamic point of view, we give some work to the gas, and then temperature goes up, right? But microscopic scopic process, how this happen?
Maybe the collision increases.
The collision increases?
In
That is what's the reason, okay? So think about it. You move the piston, right? And then you have some kinetic, when you move it, you have some kinetic energy, right? And the kinetic energy transferred to the molecule, right? And the molecule transfer to each other, they move faster, right? This is why temperature goes up. Right? As I mentioned, temperature is a measurement of the mean kinetic energy of the ideal gas. Okay? Only for ideal gas, I'm not saying that temperature is a measure of kinetic energy for all the system, okay? For the ideal gas, yes, okay? For the kinetic energy. That's the microscopic explanation, okay? Okay, so we know that with the volume going down, the pressure goes up and temperature goes up, right? Correct, everybody? And then we know that we only have two independent variables, right? The question is, how the P be changed? I mean, what's the relationship between them? We know that we only have two variables, independent variable, okay? The question is, if I compress the air for a certain amount of volume, how the pressure goes up and how the temperature changes. Okay? This is the question, okay? So in order to answer that one, so what do we know right now? What do we know that now? We know that this is ideal gas. So we have what? We have the PV equals to RT, and we only consider 1 mole, okay? So the reason is that I'm very lazy, I don't want to put N there anymore, so I'm just put R, right? But if you consider several, you just need to replace R with NR, that's it, okay? But this is only for 1 mole, okay? Just use that one for example, okay? For one mole of the gas, okay? Just because I'm lazy, nothing else, okay? We know this equation, okay? And we know that it's the adiabatic process. And it's reversible, that means there's no chemical reaction or whatever happening in the chamber. It's only gas, okay? No matter how much you compress it, there's no phase transition. You compress it, it doesn't change from gas to liquid. Or it doesn't have interaction with each other, okay? You cannot mix the hydrogen and oxygen together and press it, boom. Nothing happens, nothing like this kind of weird happens, okay? It's just like the gas, okay? Nothing changes, no chemical reaction. And we also know the du equals to what? equals to minus PdV. Correct? Right? Because we already know that del Q equals 0, right? For the adiabatic process, okay? Is that correct, everybody? So how can we solve the problem? And we also know for the ideal gas, as I mentioned, du is what? Du is the CVDT, correct? And we put them together. What we have is CVDT equals to minus PdV. Why we are doing that? Why we are doing that? We know that we have two independent variables, right? We want to know the relationship between them, okay? And you know that right now we already confine this one in the chamber. So how many variables we have? That means if we change the pressure, if we change the volume, the P and the T should be determined already, right? That means for this specific case, we only have one independent variable. Correct, everybody? We only have one independent variable, right? Because we already defined this reversible adiabatic process. Then we remove this degree of freedom. We remove this degree of freedom. Then there's only one independent parameter for this system anymore. Correct, everybody? But we cannot find the relation between them only by this equation, right? We have three parameters, and we want to solve the equation. How many equations we want to have? If we want to solve for example, if we want to know the V as function P or V as function T, we have three parameters. That means the degree of freedom of this system has these three, right? But right now we know for this specific problem, the degree of freedom is only one. So how many equations we need to build the relationship? We need two equations, right? Right now we already have one equation, right? And the purpose we are doing that one is because we want to find another relationship, okay? And the other relationship is this one. Think about it. For that one, we know the relationship between P, T, and V, and for that one, we know the T, P, and V. Okay, we put them together, we should be able to solve the equation, okay? How to do the job? We do it that way. So this is the first equation we have, and for that one, we do the full derivative, PV dP times V plus P times dV equals to R dt. This is the second equation, okay? And we put the dt in that one. Then we have dP times V plus P times dV equals to R times P dV minus, okay, divided by C. Yes. Is that right, everybody? Is that right? Don't bother. This is make the job more complicated. Let me see what's the easiest way to do the job. Okay, this is the easier way to do the job. No. Sorry about it. We can do an easier way. We directly put this equation into this equation. Okay? So we have CV dt equals to what? Minus RT divided by V dV. Okay? This is easier. Right? We directly put this equation into here. Substitute the P with this equation. Okay? Then what do we have? We need to do the integration of both ends. So we have it's what? It's CV dt divided by T equals to minus R V dV. Correct, everybody? Correct? Do you know how to do the integration? What's the integration of this function? Correct? Then when we do the integration, we need to match both ends. We need to match both ends. Okay. So think about it. At the beginning, the initial state is T1, V1, and the final state is T2, V2. Okay. So when we do the integration from the initial state to the final state, from initial state to the final state, okay? And once again, really important, we can only do the integration for the thermodynamic parameters, okay? We typically do not do the integration for this one, okay? Because this one is not a full derivative. If you do the integration, typically it doesn't work, okay? We even cannot define the loop, the path, okay? But if this is thermodynamic parameters, we only care about the first initial and final state. Then we can do the integration, okay? And for that one, what do we have? We have CV ln T2 T1 equals to minus R times ln V2 V1. Yeah, something like this. Correct, everybody? And of course, this one equals to what? R times ln V1 V2. Okay, we have negative sign. We need to flip this fraction, right? Of course, you can further just use this one. That means what? I just copy what I in my book, okay? So this one do not need to, this one is just about the calculus. There's nothing about the thermodynamic anyway. So I just copy what's in my calculation.
Is that times CV or?
It's not times CV. It's to the order of CV. It's on the corner. Okay? Then we know that the T2 equals to R divided by T2 V2, right? And also T1 equals to P1 V1 R, right? We put it into this equation, then we have P2 V2 divided by P1 V1 equals to the order of CV equal to V1, V2 to the order of R. Okay? And of course, from that one, we can have the P2, P1 to the order of CV equals to V1, V2 to the order of the R plus 1. No. R plus CV. Okay. Right? And then this term, what is R plus CV? Is CP. Or in other words, is the P1 V2 and then we can rewrite this one something like this. Is the P2 P1 equals to P1 2 divided by to the order of CP divided by CV. Okay. Correct? And then we just introduce another parameter because CP divided by CV is gamma. Okay? This parameter is simply labeled as gamma. Okay? Then what do we have? Then we have this one, right? P2 divided by P1 equals to P1, P2 to the order of gamma. And gamma equals to CP. Okay? And then we have P1, V1 gamma equals to P2, V2 gamma constant. This is a constant. So basically, this equation we call is the adiabatic and reversible adiabatic equation. That means during the resolvable adiabatic process, the pressure times the volume to the order of gamma is constant. Okay? I give you another question, so you can do this one as a practice, okay? And for next time, I'm going to spend some time to talk about it. Probably in 2 minutes to talk about it. But first of all, just copy what I'm writing on the whiteboard, and then I leave you another question to think about it. I mean, you can find the solution on textbook. Once again, this is one extreme case. du equals to delta q minus pdv. For this one, we know that delta q equals 0. Okay, we don't consider that. All right. So another good practice for to consider, as I mentioned, to go back home, is to consider such a process. Okay, we know that the du equals to delta q minus pv, and we set this one to equal to 0. Then we have a reversible adiabatic process. What about if I'm setting this term equal to 0? This process we call it isothermal process. But of course, only for ideal gas. Okay? Only for ideal gas. I'm going to explain. So what the process looks like is this one. Okay? So again, we have a cylinder, we have a piston, but instead of cover it with a thermal isolated material, we put this one in a big reservoir, in a big tank of water. Okay? This is the water. Okay, just the water. And this one is made of high quality silver of copper. That means have the thermal exchange very effectively. Okay, we keep the water at the constant temperature. We keep the water temperature at constant. That means no matter how you change the piston, the temperature of the ideal gas inside is a constant. That's the reason we call this one the isothermal process. Okay? Iso equal thermal temperature, isothermal process, temperature doesn't change. Okay? Why I'm saying that you can express or you can interpret as the interthermal process in ideal gas as the du equals 0. What's the reason for that? Why for the isothermal process in ideal gas gives this condition that du equals 0? What's the reason for that?
Because the temperature doesn't change.
Temperature doesn't change, and u only depends on temperature. That's the reason this one equals 0, right? The question I'm asking you to do that is that this, okay? So if I press the piston downward, will the gas release heat or absorb heat? If I compress the gas, will the gas release heat or absorb heat? Release heat, right? Okay, calculate how much heat got released if I change how much heat got released if I change the volume of the gas from V1 to V2. Okay? Do the calculation. Okay. Do this job when you go back home. Okay? You can find the answer in the textbook. Again, this process we call isothermal process. Or more precisely called reversible isothermal process. All right, so before we conclude this chapter, the first law of thermodynamics, I want to give a further discussion. It's not introduced in the textbook, at least in this chapter. I have no idea whether it's mentioned in the afterward, in the following chapter, but I'm going to talk about it here. So we are talking about the ideal gas, right? We are talking about the ideal gas. The ideal gas has no potential energy, no interactions between each other, between the neighboring or between the molecules. Okay, and we also know that Cv plus R equals Cp. Okay, this is for the ideal gas, right? We know the R, right? R is what? 8.31. Number, what's the value? What's the unit? I forgot. I mean, you know that's good. Okay, I only know number 0.38. But anyway, what about this one? What about this one? I mean, of course, if you know this one, you will know that one as well, right? But what about Cv? What's the number of it? Honestly speaking, if you can just give me a random physical system, I cannot tell, right? We can measure it for sure, but typically I cannot tell. But for ideal gas, we already make quite a lot of assumption that, for example, like the partial V, partial U, partial V as a constant T is equal to 0. When we also assume that the ideal gas molecule is just a small particles with no dimension, no interaction. We already have very strong assumption. So can we calculate Cv here? That's the question. Do you know what's the answer? Anybody know what's the value of Cv? Nobody knows?
Doesn't it change?
It doesn't change. It's independent of gas type. For most of the gas, for example, helium, you can check. Helium, argon, neon, they roughly have the same heat capacity. Although the mass of each atom are totally different, but they almost have the same heat capacity. And we can calculate it very precisely. The number of the Cv for 1 mole, okay, equals to 3/2 R. And of course, for Cp is 5/2 R. Okay? So what's the reason for that? Let me do some calculation. Huh? I think we're going to touch the topic again when we talk about when we introduce the statistic mechanics. But since we mentioned so much time about CVCP, so I think probably we can talk about it here right now. Okay. We know that, and let's also answer your question: why the temperature? Why we only need to consider for the internal energy for the ideal gas? And I also mentioned that the temperature is a measurement of the mean free energy. So I'm going to explain why it's the case, okay? So we have a tank, okay? We have cylinder. We have some molecules moving inside randomly. Correct, everybody? Right? But some moving faster, some moving slower. Correct? Okay. For example, if the fire alarm right now is active, you rush to the door. You know, always somebody faster, somebody slower, right? For example, probably I'm slower because I have a larger mass. Okay, somebody going faster. The same thing to here. Okay. So for each of the molecule, what is the kinetic energy? What's the kinetic energy of the molecule? Equals to what? What's the kinetic energy? Generally speaking, what's the kinetic energy? What's the form of, what's the expression of kinetic energy? Yeah, don't be shy. You should be. What's that? More precisely. Because we're talking about 3 dimensions, right? Is that right, everybody? What about the mean free energy? Average. We just sum the kinetic energy of each of the molecule and divide by the total number of the molecule. Correct, everybody? That's the mean free energy. Is that true, everybody? But how can we know the kinetic energy of each atom? There's no way for us to know. Right? There's no way for us to know. For example, if I have how many students in this class? We have 15 students in this class. Okay? Do I know? You don't need to ask how, like, no. I just have a glance, I know the number. Very precise. Okay? Because when you do the work, I'm just kind of anyway. But everybody have your final credit for final score. I can tell the final score of each point. Okay? But think about it. If I want to evaluate the thermodynamic outcome, teaching outcome of the entire nation, can I tell the number of each student, the score of each student? I cannot tell, and I don't care. I don't care. And I care what? I care the distribution, right? The distribution always looks like what? A Gaussian distribution, okay? For example, most of the students probably around C, okay? Just a pass. And you have a tail, probably A plus. And you have another tail, probably F. Correct? This is distribution, okay? And if we got improved, we know that the peak got shifted here, okay? If we hire another professor, he even do not graduate from a university, but probably have distribution looks like this. Everybody fit, right? We do not need to know the precise or accurate number of each student. We only need to know the distribution of it. We can tell the quality of the teaching, right? And for this one, the same thing. We do not need to know the accurate kinetic energy of each molecule, but we only need to know the distribution. Actually, for the thermodynamics, you will find this is the kinetic energy. This is the number of atoms in a given state. You'll find most of the atoms have very low energy, and as the energy goes up, the higher the energy, the less molecule. You have less and less molecule have a high energy. Think about it. Typically not very energetic. Okay, most of molecules are very lazy. Okay, just like in the parking garage. Think about the parking garage. Which floor, which level you prefer to park in the parking garage? The first one. Okay? And if you go top, typically there's nothing there, right? The same thing, the same distribution. Most of our molecules are lazy. They stay at the 0 energy roughly. And then the more, I mean, if you go to higher energy, you have less and less molecules there. Okay? More precisely, the distribution looks like this. Okay? The number of particles as a function of the kinetic energy is proportional to the E to the order of negative kinetic energy divided by kT. K is the Boltzmann constant, okay? K is what? K is the R divided by Avogadro constant. Okay? That's a K, the Boltzmann constant. Okay? So follow that one. So if we know this one, okay, this one we call is the Boltzmann distribution. Okay? We're going to touch this topic again in the later class. After we talk about second law of thermodynamics, we're going to introduce this concept again. But right now, we just know the number of particles in a certain energy can be expressed in such a way. Okay? In that case, the average kinetic energy can be expressed in this way. Okay? Just sum I. Not sum I. We just sum through the kinetic energy. Okay? That is the kinetic energy that is half m x vx squared plus vy squared plus vz squared, and then e to the order of kt, and then half x squared vx squared plus vy squared plus vz squared. Okay? Think about it. This one is the kinetic energy, and this is the distribution of the kinetic energy, of the distribution of the number of particles in a given kinetic energy, and we sum them together. Right? Of course, the energy are continuously distributed, right? They are not isolated. So we replace the sum with the integration. Okay? And the dvx, dvy, and the dvz. Okay? So what's the number of particles? The number of particles is just the integration over the distribution. We do not need to consider the kinetic energy anymore. We only consider the distribution.
So we don't divide by n anymore?
Huh?
We don't divide it by n?
This is n. This is n. Right? So why? Because you know that this is the kinetic energy. This is the number of particles in a given area of kinetic energy. We just do the integration. That's the total number of particles. This expression very beautiful. Think about it. This one we have three terms, right? We have three terms: vx, vy, and vz. We can separate to three iterations, right? For example, we only consider vz. So the average vx squared equals what? We only consider that term. So the kinetic energy will become integration of half m vx squared and e minus half m vx squared plus vy squared plus vz squared, and divided by kt, and then times and then dx, dvx, dvy, and dvz. Okay, and for the bottom, integration minus half dvx, dvz, dvy, and dvz. Okay. And of course, we have another term about vy, probably plus another term is about vz. Correct, everybody? Because these three terms we can just separate into three terms. Time's up. Anyway, think about it. This term, we can also change this term to what? To e minus half m vx squared plus kt times e minus half m vy squared times kt, and e minus half m vz squared minus kt. Correct, everybody? And for the bottom, the same thing. But in the front, we only have vx. It's independent of vy and vz, correct? So we can simplify the equation in such a way. Because all of them just cancel each other. Correct? So what? So the kinetic energy eventually become half m3x squared plus half m3y squared plus half m3z squared. Okay? That's good again. Okay, so time's up. So I'm probably continue next time. And the conclusion is for each of the term, we have the average equals to kt. Each of term has an average of kt. So we have three terms, so we have 3.5 kt. Okay? So that this called the theorem. Okay, there's a theorem called what? What's the name of it? Okay. It's called the equipartition theory. That means in the energy term, as long as you have a square term, each of the square term will contribute the heat capacity of the half kT. Okay? You know what I'm saying? Oh, I'm sorry. So for the half RT, okay? For the half RT, this is water capacity. So I'm going to finish the proof next time during the class. Okay? That's the first thing we're going to do. And we're going to briefly talk about the isothermal process. After that, we enter the next chapter, the second law of thermodynamics. But first of all, I'll give you a hint. Try your best to finish the integration after you go back home. Okay? So one trick we call is the Gaussian integration. You want to use that one to finish the job. Okay? Gaussian integration. Okay? Try to use that one to calculate the expression. Anyway, so we're going to continue next time. Probably having this kind of nice time.